Okay, so we have seen a couple of examples that talk about a constant rate of change, but we really haven't talked about what slope is. So let's work on that. So example 3, the population of a city started at 4,000 people in the year 2000, and it's been growing. Okay, so right off the bat, I'm not sure what's going to be asked of us, but I can see a pattern. So I'm going to jot it down quick. I see that every additional year, this population is going up 30. Okay, so just so that we see the pattern, okay, got it. Number 1, for each additional year that goes by, what happens to the pattern? Well, luckily, that's where my head game was. Not necessarily on purpose, but I just was looking at these numbers and I noticed, oh, I see what's happening here. So for each additional year that goes by, what happens? Increase by 30. Is this model linear or exponential? How can you tell? It is linear because it is a constant addition of 30 each year. Explain what the ordered pair 4 along with 4,120 means in this situation. Oh, okay. Well, this is T for time, or this is the time, okay. So hold on, let me label a couple of things. This is years and this is the population. And this was years since 2000. So 4 years after 2000. So in 2004, was it a town, a city? Okay, whatever. The city's population was 4,120 people. 4,120 people in 2004. That's what this ordered pair refers to. So 4 years after 2000, there were 4,120 people in the city. Yeah? Okay. Fill in the table with the ratio of change so change in population to change in years. Okay, so we're creating a ratio, change in population compared to the change in years. Got it. Let's do it. From 2000 to 2004, the change in years, 4 years. And the change in population went from 4,000 to 4,120. The new population is 4,120. The old population, the original, was 4,000. So that's a change of 120, I'm going to call it people. If we turn this into a unit ratio, each of these are divisible by 4. That would be 30 people in 1 year. 30 people per year. Got it. Let's do this one now. Okay, so the change in time, so the change in years, it goes from 2003 to 2005, so it's increased by 2 years. And change in population, it went from originally 4,090 to now 4,150. That is a change in 60 people. Okay, and if I turn that into a unit ratio, both are divisible by 2. So scale down by 2, that's 30 people. Scale down by 2 in 1 year. 30 people per year. Okay, let's do it again. From 2001 to 2002, so that is a change of 1 year. It went from 4,030 originally to 4,060 after a year. So the change in people, 30 people. And that is actually already a unit ratio. 30 people in 1 year. Okay, here we go. So we found our ratios. What do we notice about the ratios? Well, here's the thing. Regardless of what ordered pairs you compare or what times you compare, if you write these as a ratio, the change in population compared to the change in time, you get the same unit ratio that we were kind of talking about up here. For each additional year that goes by, the population increases by 30. So what do we notice about the ratios? If we simplify them, they all boil down to the rate of change in population per year. So what do we notice? They all simplify to the same unit ratio of 30 people per year. Or we could have called that the rate of increase. So that brings us to the slope of a line. Let's define that. Okay. We'll go green style. So to me, the slope of a line is a ratio, and this ratio is the response variable change. Okay, so change in population, change in the response variable, to the explanatory change. I'm going to run out of space. Of course. So the response variables change as a ratio compared to the explanatory variables change. And a lot of people like to write it like this. So change in response, or the dependent variable, response. I almost misspelled that. Change in dependent variable as a ratio to the change in explanatory variable, or independent. Okay, also known as the change in the y values compared to the change in the x values if you're using y's and x's. Y's for your responding variables and x's for your explanatory variables. And that's why a lot of times you will see this written as, when we were finding the change, we did a subtraction. We found literally, going back, the new amount minus the original amount. The new y value minus the original y value. Okay, so they are using these change as y1 and y2, or what have you, actually probably y2 minus y1. But I need you to know that that just really boils down to this idea of change. How much did it change? So the formula you will see people give are these subtractions, y2 minus y1, but that's just the change in the responding variable, the change in the population. And x2 minus x1, that is a change in the explanatory variable, or in this case, the change in the years. So the slope of the line is really just this constant ratio, or this constant rate of change of the response variable to the explanatory variable. A couple of remarks. First, if the graph of a line is a line, if the graph creates a line, okay, so the image of the relationship is linear, then m. Okay, then the slope is the same regardless of the points we chose to compare. Regardless of the coordinates chosen. Okay, so if it is linear, it will always simplify down to this unit, the same unit ratio. Okay, if it's not linear, that won't happen. It won't simplify to the same unit ratio. Okay, another remark. If the graph is a line, slope will not vary. So I'm going to write down exactly what we just said. So this, if it creates, it shouldn't matter what coordinates you pick or ordered pairs you pick, because this unit ratio will always be the same. But let's write that down. So this is just saying you can choose any ordered pairs you want to, and it'll still reach you to the same slope if it's a line. And then the next one, my next remark is if the graph is linear. So again, if all of the data lines up into a line, this rate of change will not vary. It is this constant increase by 30 each year, plus by 30 each year. The unit ratio is 30 people per year. If it's linear, that will not vary, because that is actually the constant addition, or subtraction. If not linear, this computation, this comparison of change in the response to change in the explanatory will vary. If not linear, then this computation, this ratio, it'll be different for each, not for every, but for the majority or a lot of ordered pairs that you pick. This unit ratio would be different. Okay, and then slope is often interpreted as the rate of change. Or the constant rate of change. And since it's not varying, that's where the word constant comes into play. Slope is the constant rate of change. In other words, how quickly is something changing? It's changing by 30 people per year. Okay, so let's talk about rates. If rates are slopes and slopes are rates, let's talk about them quick. A person gets paid $100 a day. How much will they make in a 5-day work week? Write this as a ratio with labels. Okay, so here is a rate, and the slope would be $100 per day. So this ratio, so here would be our constant rate of pay, and we would call this the slope. How much will they make in a 5-day work week? Well, this is scalable. So $100 per day. What are they doing? Like flooring? That's a lot. Is that a lot? I don't know. That's like working for 5 hours at $20 an hour. Anyway. $100 for 1 day. Scale this up. Make an equivalent ratio. If I did that 5 times, then I get paid 5 times. Scale up, $500. And then it asks, how much do they get paid for 0 days worked? Well, scale it down by 0, scale it down by 0, $0 per day. So at $100 per day, that is $0 for 0 days. Okay, and now that's awkward because I was about ready to write this 0 over 0 days. And as a fraction, that doesn't make any old sense. But as a ratio, it sure does. So just to put a little shout out to this whole like 0 divided by 0, which is an error, and I even talked about that in my fraction video. But here, as a ratio, it's okay because this is really being interpreted like this as opposed to a division problem. So, FYI. Number 2, write a unit rate that is equivalent to 60 miles in 4 hours. Okay, we can just scale this down. And it says unit, which means one of these has to be a 1. Let's see, if we have 60, so our constant rate of change is 60 miles in 4 hours. Let's scale it down by 2. Because if I bundle up these into 2s, then I have 2 hours. If I bundle 60 into 2s, that's 30 miles. Okay, so I just scaled down, took half and half. Okay. Or if you want to write divide by 2, fine. Oh, okay, well, that is scale. I can scale that down by 2 as well. So scale this, that means in 1 hour, half of 30 is 15 miles. Okay, and there's our unit rate, 15 miles per hour. Maybe that's a bicycle. Anyway, one cyclist pedals at a rate of 40 miles in 3 hours. Another goes at the speed of 50 miles in 4 hours. Which is faster? Show how you know. Oh, okay. Here we go. Pedalist number 1, 40 miles in 3 hours. That's their rate. Another, theirs is, okay, so versus 50 miles in 4 hours. Okie dokie. Yeah, this is really hard to say because this is going 40 miles, which is fewer miles, but in 3 hours, which is fewer hours, which makes perfect sense that in fewer hours you have traveled fewer miles. It's just talking about their speed or their rate. Believe it or not, I'm going to scale these up instead of scaling them down because I want to see if they were able to keep this up for 12 hours, which is, by the way, seemingly impossible. Then this one would be, let's see, scale this up by 4. In 12 hours, they would go 160 miles. That first cyclist. If we scale 50 miles up, 50 miles in 4 hours up by 3, then in 12 hours, this cyclist would have gone 150 miles. Okay. Which is faster? 40 miles in 3 hours. Now, if you had, instead of gone up to 12 hours, which is a little bit like, whoa, if you had scaled this down to a unit ratio, that would have made sense too. I just knew that 3 didn't go into 40 well, and so I didn't scale it down, but you could honestly find their unit ratio and compare those. How many miles are they going per hour? Will a cyclist pedaling rate stay constant after many, many hours? No. I don't think so. Let's go blue style. No way. What effect does that have? It's not going to be a constant rate. So that means it's not going to be linear. So the graph of the miles the miles ridden by a cyclist is not going to be linear, because there's no way they can keep up this rate at a constant rate. So no, what effect does that have? So if it's not a constant rate, then the graph of miles ridden will not be linear. Okay, so quick summary. Let's go back to go forward. Quick summary. Patterns, so model some patterns with a constant rate of change, or a constant addition, or a constant subtraction. Well, we figured out those patterns are actually both linear from previous discussion, and we also found out that that constant rate of change is the slope. They're one and the same, and that this constant rate of change is really a constant ratio of change. It just got changed. I mean, it just got reworded. Instead of saying constant ratio of changes, now we say constant rate of change. And then instead of saying constant rate of change, we said, okay, what's the slope? Okay, so these all are actually the same thing. And if it's a constant ratio, then that will be the slope of a linear situation. So a situation where the graph will look like a line. All right. Until next time.